G'day guys, and welcome to our lesson on transformers. You use a transformer when you've got a power supply, which is AC, and it's operating at some voltage, but that's not the voltage you want. You want another voltage. So a transformer allows you to maintain the same power, but change the voltage of a supply. A transformer is made up of an iron core, pictured here. Iron core. It is made up of, well, here we have the primary coil, so a wire that loops around one arm of that core. And if it's the primary coil, it's the coil which is supplied by the AC power source here. Then we have the secondary coil, and that's the coil with the load on it. So we'll put a resistor here. And we'll leave the switch open for now. And that coil does much the same. It wraps around the iron core like that. And what the transformer enables us to do is to have power generated by that circuit there transferred into this circuit here. And it's not as though the current is running through the iron core. Instead, since this is a coil here, and we learned in our lesson on magnetic induction, that if you change the voltage through this coil here, the magnetic field caused by the current will also be changing. And if the magnetic field is changing over here, it will also be changing through this loop here. So by generating a change in current through this coil here, you generate a change in magnetic field here and here, and the change in magnetic field here creates a change in flux through these loops, which generates, when this switch is closed, a current through this circuit here. Now the key to a transformer, we said that's one way to take power from this circuit to this circuit here. But I said before, it changes the voltage. Changes the voltage. And the way it changes the voltage is determined by the number of loops here and the number of loops here. So we'll call this big N, secondary, the number of loops on the secondary coil, and here the number of loops on the primary coil. Also notice there's a voltage for this circuit here, V primary, and a voltage for this secondary circuit here, a voltage that is available to the whole circuit, Vs and Vp. Now Vp is different to Vs if Np and Ns is different. So the basic principle is, if you have a lot more loops on this coil here than this coil here, Vs will be greater than Vp. If Np, if the number of loops on this coil is greater than the number of loops on this coil, Vp will be greater than Vs. So let's look first of all at what would happen if I left this switch open here and supplied an AC power through this circuit and coil. Well, first of all, the current would be jumping back and forth in direction. It would be generating a magnetic field which is changing through itself, so backwards and forwards and backwards and forwards. And what would happen, as long as I left this switch open, if it's a good transformer, that changing magnetic field in here will not allow any current really to flow through this coil. It seems like a bit of a contradiction, but basically when the current changes, it creates a magnetic field change which resists that change. So as long as this switch is open and no current can possibly flow through that circuit there, you get zero current flowing through this circuit. Let's look what happens when I close this switch though. Now, if I have an AC current going through here, and the current suddenly increases in that direction there, magnetic field lines using the right-hand grip rule will be flowing down through this coil here and up on the outside. So we get a sudden magnetic field flowing like that through also the iron core. That means over on this coil here, this blue line going through the middle of those green loops, since there's a changing flux through those green loops, we experience a voltage in this circuit. And if we want to resist that change in flux, we'd run current in that direction there. So this is drawn a little strangely, but it would flow like that there. So the AC signal, it's just increased in this direction, and we've seen a boost in current over here in this direction. Since this signal is AC though, the direction of that current will now reverse. So it was going in that direction, now it's going to swap to this direction. And all of a sudden, the magnetic field lines run in the opposite direction, that way. And if we were to resist that change, the current is now going to be running in this direction here. So in that way, AC current in this coil creates an AC current in this coil over here. Let's say there were 50 loops over here and only 10 loops over here. And the voltage we're putting in is equal to 2 volts. Using this equation up here, Vs on Vp is equal to Ns on Np. We can figure out how much voltage is being put through that circuit there. So first of all, Vs is what we want to find. Vs over Vp, that's 2 volts, is equal to Ns, 50, over Np, 10. Getting Vs by itself, 2 times 5, 10 volts. So since there are more loops on this coil than this coil, there's more voltage around this circuit than this circuit here. This is known as a step-up transformer. However, erasing this bit of work here, if I swap the number of loops around, and I say on the first coil there was 50, on the primary coil there's 50 loops, on the secondary coil there's only 10 loops. Now Vs over Vp equals Ns over Np, that still holds. Vs, the mystery, over 2 is equal to Ns, 10, over 50. Vs equals 2 times 10 on 50, which is 2 times 1/5, or 0.4 volts. So since there's fewer loops on this coil than this coil, the voltage has decreased from 2 volts to 0.4 volts. This is known as a step-down transformer. So that is one part of transformers, that formula there. Here is the other key. The power in the primary coil is equal to the power in the secondary coil. In other words, Vp times Ip, which is the primary voltage, not the peak voltage, multiplied by the primary current, is equal to Vs times Is. But we just said we boosted up the voltage, or in this case we've decreased the voltage over here. If both of these sides have to still be equal, then we have to actually increase the current as well. So when you drop the voltage over a transformer and you don't lose power, and in really good transformers, not ideal, in really good transformers, you only lose about 1% of the power. If you drop the voltage, the current will increase. So even though there's less voltage in this circuit here, there's a lot more current flowing through it. Let's do an example question. No, let's look at how the current changes. That's right. If I get Is over Ip, so rearrange Vp over Vs is equal to Is over Ip, and we knew Vp over Vs, well, I'll swap both these around, Vs on Vp is equal to Ip on IS, VS on VP is equal to NS on NP. So the other formula we could use is that the ratio of the secondary number of loops here to the primary number of loops is equal to the ratio of the primary current to the secondary current. Whereas notice here it's primary current and secondary voltage on top over there. It might be easier just to use this formula here, at least that's what I think. So say we've got a speaker, and the speaker has got a transformer connected to it. So that would be the secondary coil, and this would be the primary coil here, because this is the power supply. And the speaker runs on 60 volts, and the power supply is 240 volts. Talking, of course, in VRMS here. So this is technically the primary VRMS. If there are 80 loops on the primary coil here, NP equals 80. Let's figure out how many loops are on this secondary coil here. And if the speaker, if the mains have a 2 amp current, let's figure out the current in here. So NS is equal to, and IS is equal to. Well, first of all, VS on VP is equal to NS on NP. So 60 VS on VP 240 is equal to NS, we don't know, over NP 80. Get NS by itself, 60 on 240 times 80 is equal to 1/4 times 80. There must be 20 loops here, and this is a step down transformer. So NS is equal to 20. IS is equal to, well, the power here has to equal the power here. So 240 times 2 has to equal 60 times IS. 480 equals 60 times IS. 480 over 60 is equal to 8 amps. So see here, the voltage has gone down. It's a step down transformer. There are fewer loops on the secondary coil than on the primary coil. But since we want the power to remain constant, if the voltage has gone down, the current here has to go up. So there's considerable current going through that speaker there. Another way to think of it, if the voltage has gone down by a factor of 4, the current must go up by the same factor. So to summarize this lesson, the number of loops on this side of the transformer, the ratio of the number of loops here to here, tells you the change in AC voltage from the primary to the secondary. And the secondary's got the load and the primary's got the power supply. Furthermore, if power is constant, and power is pretty much close to constant in reality, you can also tell how the current is changing from this circuit to this circuit here.